Okay, so we're going to take a look at one more example of graphing vector valued functions in space. And this example is the helix. I have a very hard time graphing this one, but I picked it because I have a diagram to show you and also because I'm going to make use of projections and show you how to do that. So in order to graph this vector valued function, it's r of t equals negative sine t cosine t and t for t greater than or equal to 0, I'm going to use projections. And what that means is I want to see what is the projection of the curve on each coordinate plane. So we're going to explore what is the xy projection. And to do that, we're going to let z equal 0 so we can see kind of what the shadow is that the curve creates on the xy plane. We're going to take a look at the xz projection, and for that we're going to set our y equal to 0. And so that's going to mean what is the shadow of the curve on the xz plane, and then we'll also look at the projection on the yz plane, the yz projection, where we set x equal to 0. So let's start with the xy projection. So this is projecting onto the xy plane. When z is 0, our vector function becomes r of t equals negative sine t, cosine t, and 0. And we can graph this on the xy coordinate system. So that's what we're going to focus on. Here's my xy coordinate system, and let's take a look at what we have for our x and y components. We can see here that x of t is negative sine t, and y of t is cosine t. And that's, of course, for t greater than or equal to 0. This is actually a clockwise rotation around a unit circle. To see why, let's think about our starting point. When t is 0, so when t is 0, sine x will be negative sine of 0, which is 0, and y will be cosine of 0, which is 1. So we're starting with a vector that points to the point on the y-axis 0, 1. If we increase t, maybe we'll let t be pi over 2, then x will be negative sine of pi over 2. Sine of pi over 2 is 1, so this is negative 1. And y will be cosine of pi over 2, so that's 0. Actually, yeah, negative 1, 0. It is going to go in the counterclockwise direction. I said clockwise. It looks like it's going to travel in the counterclockwise direction. I said clockwise because I was thinking positive sign. So let's change that. It should be counterclockwise. Looks like we're going in this direction, counterclockwise. Let's just test again. When t is pi, we can see that x is going to be 0 and y will be negative 1. So yes, we're definitely going counterclockwise. And this is a unit circle in the counterclockwise direction. There we go. So because of that negative sign, this is counterclockwise. Let's take a look at the xz projection. So I'm going to move this graph a little bit down further. We'll get to that in a second. And we're going to look at the xz projection. And to do that, I want to see what the shadow of my curve is on the xz plane. So I'm going to let y be 0. That gives me my vector function will become negative sine t, 0, and t. Again, t greater than or equal to 0. So that means we have x is negative sine t, and z is equal to t. If we use these two equations and eliminate our parameter, we have that x equals negative sine of z. So this is a sine function that's been reflected and it travels along the z-axis. If we think about our projection here on the xz plane, it depends on what I decide is which axis, right? I'm going to choose my x-axis to be the horizontal axis and my z-axis to be the vertical. And this is going to travel along the z-axis, and it's negative sign. So maybe we should put in a few points so I don't make a mistake. So when t is 0, that's where we start, we would get negative sign of 0. So the x-coordinate of the head of the first vector will be 0 and y is 0. So we start at the origin. Let's say when t is equal to pi over 2, our components will be, a point, the head of the vector would be negative sign of pi over 2 will be negative 1, and t and z would be pi over 2. So here's what's going on. If this is pi over 2, we're going to be down here. So we have a graph that's going to look like this, right? It's a sine function that's been flipped over the z-axis because of the negative sign. So that's our xz projection. Let's take a little time to find the yz projection, and then we'll compare it to the image of the helix. So our yz plane means that we're going to let x be 0. So when x is 0, our vector function becomes 0. I think it was cosine t and t, which gives us that y is cosine of t, z is equal to t. Eliminating our parameter, we have y is cosine of z. And z must be positive because t is positive. So if we, again, try to sketch this projection onto the yz plane, let's do that. I'm going to use a white marker here, and I'm also going to let y be the horizontal axis and z be the vertical axis. I generally let z be the vertical axis no matter what the horizontal axis is. And we have y as cosine. So cosine of 0 is 1. So when t is 0, we're going to start here, and we're going to generate the cosine function, but only for values of t greater than 0, so z must be positive. So there's our cosine. Now, this is what's very difficult to do, is to put all of these projections together. So I'm going to bring up this image and show you each of these projections and what it creates. Oops. Let me rotate it back. Here we go. So you can see that our xy projection is that circle. And remember that we're traveling counterclockwise. Our yz projection was the cosine function. It's right here. And the xz projection was the negative sine function right here. Notice that they're both the cosine and the negative sine are traveling along z. As t is increasing, z is increasing, and the actual curve is called the helix. And it is this curve. Just follow my little dot. That is our helix. Keeps curling up. So that's how we graph a vector function using projections.